Hello, gentlemen, and welcome to section 6.3, Chemical Names and Formulas. A lot of this is review, but there are some new things towards the end, so please take adequate notes. When we're naming different compounds, we have different methods. The first one we'll talk about naming ionic compounds. First off, ionic compounds are made of ions, cations, and anions. Cations are positively charged atoms, anions are negatively charged atoms. Review your notes on ions to know more about that. Cations are usually metals, and anions are usually nonmetals. Now, an example, magnesium and chlorine bond together. We know magnesium's Mg, it's found in group number 2, has 2 valence electrons. It's going to lose those 2 valence electrons as in a metal and become a cation, Mg2+. It's Mg2+ because it has 2 fewer electrons than it does protons. Protons win by 2. Chlorine is in group 17A or 7A and it has 7 valence electrons. Elemental symbol Cl is going to be Cl1- because it's going to gain 1 electron to achieve an octet. Magnesium lost 2 electrons to achieve an octet. Do the crossover method and we get, I'll draw it over here, MgCl2. So 1 goes to the Mg, 2 goes to Cl. That should be reviewed. When we name this, we name it the first name of my cation, which is magnesium, just its name. And then we add to it the name of my second atom with an IDE ending. So chlorine goes to chloride, magnesium chloride. That's how we would name that. That's an ionic compound. We also know that we have polyatomic ions as well that can form ionic compounds. So my polyatomic ions, examples would be hydroxide, OH-, sulfate, SO4, 2-, carbonate, CO3, 2-, and ammonium, which is NH4+. These are our polyatomic ions. They're also made of cations and anions. Polyatomic ions are essentially covalently bonded atoms that have a charge. Now, how does it look when it's being named or the formula is being drawn for it? Very similar to ionic compounds with monatomic ions. So magnesium, it's still Mg2+. Hydroxide, we look at our polyatomic ion chart, we find hydroxide, and we write it just as is, OH-. Now we use the crossover method here. I write the compound here. Magnesium gets the 1. Hydroxide gets 2. So it takes 2 hydroxide polyatomic ions to satisfy that 1 magnesium. This creates an electrically neutral compound. And we name this name and name. So we take the name of 1, magnesium, and we add to it the name of the other one, hydroxide. This is with polyatomic ions, magnesium hydroxide. When ions are dissolved in a solvent, they form electrolytes when they're in solution. Remember that. Now, if we don't have ionic compounds, we've talked about molecular compounds. A molecular compound is when you have 2 or more atoms bonded together by sharing electrons. We haven't talked much about molecular compounds with that terminology. This terminology is very similar to what we've been talking about with compounds. Compounds are just 2 or more different atoms bonded, but with molecular compounds, it's specific, meaning it's when they're bonded through sharing electrons, or meaning they're covalently bonded. So atoms that are covalently bonded are molecular compounds. Ionic compounds would not be considered molecular compounds. Okay, when we have a molecular compound, it's usually from a nonmetal bonding with another nonmetal. Some examples would be carbon dioxide, CO2, H2O, C2H6O. These are my chemical formulas. When naming these formulas, we use prefixes and a suffix as an IDE ending. So we name using prefixes. The prefixes are mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. These are in numerical order from 1 being mono to 10 being deca. After we add our prefixes to the second element, we add an IDE ending. Let's go through that now. So for CO2, if my first element only has 1 atom, if it's only 1 atom in my first element, I don't write mono, I simply write the elemental name. In this case, carbon. I have 2 oxygens, so I put di for 2, and I change the ending to IDE, carbon dioxide. H2O. I have 2 hydrogens, so I write di for 2, and I keep the name the same, dihydrogen. And O, I have 1 O, so I write mono, and I change the ending oxygen to IDE, so monoxide. This is all review. Now this element here, I can't name it using this system. You can only use this system when you're naming binary compounds. Binary compounds means that I only have 2 atoms, or sorry, 2 different elements existing in my compound. Here I have 3. I can't name it using this system. Thus, we use a different system for that, which we haven't learned yet. Now, molecular compounds do not form electrolyte solutions. They do not dissolve in water to form compounds that can conduct electricity. They're not ions. There are no ions in this molecular compound solution, thus no electrolytes. Now, one concept that we talked about in our investigate is oxidation numbers. So an oxidation number essentially is a number assigned to an element in a compound designating the number of electrons the element has lost, gained, or shared in forming that particular compound. We'll talk about why shared is underlined momentarily. Now, let's do some examples of this. That's the best way to do it, is just with examples. Oxygen, element O. When it goes to achieve an octet, it's going to gain 2 electrons. It has 6 valence electrons. It's going to gain 2 to achieve an octet. When it does so, it becomes O2 minus. Its oxidation number, we would say, is 2 minus, or minus 2. So its oxidation number is 2 minus. Now, how does this apply with compounds? Let's see. My example down here, calcium oxide. I know that calcium, when it forms an octet, will give away 2 valence electrons and form Ca2+. Oxygen, up here, it's going to form O2 minus because it gains 2 valence electrons. So 2 plus and 2 minus are oxidation numbers. Notice when these 2 oxidation numbers add to each other, they cancel each other out. That's why we have no subscripts here. And this is how many electrons that were lost or gained. Now, this is an ionic compound. This is just a single atom in an ionic compound. Let's see what it looks like in an imaginary compound. Here. Sorry, not an imaginary compound, in a molecular compound. Excuse me. Carbon dioxide is in a molecular compound. And we call its oxidation numbers imaginary because it didn't really lose electrons or gain electrons. It's sharing. That's why sharing here is underlined. So sharing kind of alludes to imaginary oxidation numbers. So let's think about it in this way. Oxygen. Oxygen, when it achieves an octet, is going to gain 2 electrons. When it gains 2 electrons, it's going to become O2 minus. In this compound here, I have 2 oxygens. So I'm going to have 2 minus, oxidation of 2 minus, but I'm going to have 2 atoms. So 2 of these 2 minus charges giving me, say, 4 minus. Now I know that this compound is electrically neutral. There's no charge. When I breathe out carbon dioxide, I can't conduct electricity. So I have a very neutral compound that's produced. So carbon has to balance out that 4 minus charge. Thus, carbon's oxidation number has to be 4 plus. The 4 plus and the 4 minus are the oxidation states, we call them, for carbon and oxygen. And when they add together, they make a neutral compound of 0 charge. That's oxidation numbers. Now, we find this most readily, and it becomes very helpful when we talk about naming transition metals. We name transition metals that are bonded in ionic compounds with a system called the stock system naming method. This is where we use Roman numerals to represent the oxidation states of various metals. Now, if we remember, our transition metals are here in the middle, in our D block, if we're talking about orbitals. Now, if we remember, we also were able to figure out the oxidation states of other metals by using the group number. So elements in group 1A had an oxidation state of 1+. Group 2A, 2+. Group 3A, 3+. So those metals found in those groups, you could easily identify them based on the number of valence electrons and the group number. With transition metals, it's not so easy. When you think about what charge do they form, we don't really know. It's a question. They're called transition metals because they can transition between different oxidation states. Sometimes they may be 1+, sometimes it might be 2+, sometimes they're 3+, sometimes they're 5+. It depends on the situation. So we use Roman numerals in the chemical names of these compounds to represent what oxidation state they're actually in. So here's an example. Fe2O3. What's the name of that? Well, first thing to do is figure out the charges of these. We know the crossover method is used to get ionic compounds into their formula state. Let's uncross this to see exactly where this came from. This 3 goes back to the Fe, so we get Fe 3+. We know it's 3+ because our cation always comes first, and metals always form cations. This oxygen gets O2-. We know oxygen is O2-, oxygen is in group 6A, it's going to gain 2 valence electrons and always be O2-. So this 3+ is the oxidation number or oxidation state of iron. Iron has an oxidation state of 3+. Oxygen has an oxidation state of 2-. When I write the chemical name of this, this is going to be called, I write the first name, just as I would in all ionic compounds, iron 3. I put my 3 in parentheses and in Roman numerals to represent the oxidation state of this particular iron. So iron 3 oxide, also known as rust. And we only put Roman numerals in the name. We never put it in the formula. Never ever will you put a Roman numeral up here as a charge or as a subscript. It only goes in the name. And if I have a name like nickel 2 bromide, I can deduce what the oxidation state of nickel is from my Roman numeral. I know Nicholas is Ni. 2 stands for its oxidation state or its charge. Nickel 2+. It's going to be positive again because metals form cations. Bromide, we know bromine is Br. It's in group 7A. It's going to gain 1 valence electron and become Br-. So I do my crossover method. I get NiBr2. That would be nickel 2 bromide. And you would say it that way, nickel 2 bromide. Not nickel bromide, but nickel 2 bromide. There are some exceptions to the rule. There are some elements that always have the same charge, no matter what. They don't transition. One is silver. Silver is always 1+. Zinc is always 2+. Cadmium is always 2+. Silver is here. Zinc, cadmium. One way to remember this is we know that aluminum is here. Aluminum always has a charge of 3+. If you just go down the staircase this way, it's aluminum 3+, zinc 2+, cadmium right under zinc is 2+, and silver is 1+. So it's kind of like 3, 2, 1. It's a good way to remember it. We also use the stock system naming method with elements in group 4A at the bottom. Metals here in group 4A, they're in my other metals category down here at the bottom. Namely Sn, which is tin, and Pb, which is lead. So gentlemen, hopefully this helps. We're going to be doing some practice with this shortly, and this is going to help you step your game up when naming different compounds in chemistry. Take good notes, gents.